Dadme un segundo que vamos a cablear al ponente. Muy bien, muy bien, muy bien. Next speaker came from Checkpoint. He's Dario Durando. Oh, sorry, Fortinet. Excuse me. I have a mix on sponsors today, but really bad. Don't take this in count. He will talk about IoT, the battle of the bots. It is really interesting. So Dario, introduce yourself and please the screen and check everything is right. Okay, thank you.
Yeah, it's all right. Thank you very much. Hi, everybody. The talk is going to be about botnets, specifically Mirai, if you are familiar with that. I am Dario Durando. I am a researcher at FortiGuard Labs, and I focus on Android and IoT malware research. And so what we're going to talk about today is an overview of how Mirai botnet works, and then I'm going to go on about how the lab we set up works, and then a brief talk about the new variants that we discovered or that are the most interesting. So first of all, if you don't know what Mirai is a botnet that appeared the first time in mid 2016. It is the biggest at the moment in terms of bots pulled, and it was made open source, or let's say the source code was released by its author, a user going by the name of Anna Senpai on a hacking forum in September 2016. So now I'm going to briefly explain how the botnet actually works. And be kind with me, I'm not an artist, I'm an engineer, so the PowerPoint is going to look weird, but thanks. So we start with an infected IoT device, the one on the bottom left. So what this device will do is to try to gather other vulnerable devices and add them to the botnet. So it will try to brute force the login of other devices, and if it manages to get a login in the device, it means the device is vulnerable. So we'll report the credentials, the IP of the bot to the report server. The report server will pass this information to the loader, which will directly load the bot on the vulnerable devices using these credentials. Once the bot is loaded, the vulnerable device becomes infected, and it will basically be part of the botnet. So it will again try to add new bots. So we'll start brute force other IPs, and at the same time it will report to the server with its credentials that will be added to a database with all the bots. Then this database, including all the bots, can be used by different users that have access to the botnet to start an attack. So we'll send an attack command to the C2 server. The C2 server will decide which bots to use for this attack, how many. I mean, it will be prompted on how many. It will pass the command to the infected devices of choice, and then they will attack the target. So it's very simple, it's very straightforward. The modules that compose the botnet are the C2 server, which is in charge of creating the different sets of bots that are used by different users, add new users, because we have to remember this is basically a way to make money for the admin of the botnet, so it can create a user for a specific guy that wants to use the botnet to attack someone. And it's code all in Go and supports telnet, authentication, or API keys. So the second module is scan listener. This module serves the purpose of receiving reports of vulnerable IoT devices by the bots in the botnet. It listens on port 48101, and receives these IP and credentials that are then passed to the loader, which, as I said, logins with these credentials into the device, and then uploads the bot code using different methods. It could use wget, it could use FTP, or could even just straight up use echo and save it. The bot instead is coded in C, and it is cross-platform compatible. Here it says x86, ARM, MIPS, supports others, supports Super H, supports ARC recently. And it's made up of three major modules: the scanner module, the attack module, and the killer module. The scan module is in charge of finding new bots, new possible bots. So it will generate an IP, a random IP, and this IP is generated randomly, but tries to avoid the list that you can see on the right, on the top there. And this list comprises of non-valid or useless addresses like loopback, but also some government-associated IPs and some big companies like HP. And this is the whole list, by the way. It's not that many, so it's kind of pointless in my opinion, but it's there. And then tries to use the credentials that are hard-coded in the bot to log in. These credentials range from like root, admin, to like the first one, XC3511. It's the default password for Xiaomi, which is a Chinese brand of Wi-Fi cameras, and VizXV is Dahua. So it's just known passwords that are hard-coded in these devices. The attack module contains all the different attacks. It's an implementation, can run UDP attacks, TCP attacks, HTTP, all the different kinds. And it's up to the user to decide which one to use. And then once that happens, the attack is perpetrated. The final module is the killer module. And this module is what kind of makes Mirai stand out among all the other bots, because it shows the aggressiveness of this bot. What it does, it tries to kill any process that is trying to use these three ports: the telnet port, the SSH port, and the HTTP port. So once the bot infects a device, it effectively does not give the opportunity to be infected again by some other bot using these ports. And also has a lot of hate for other bots. Here it tries to detect Qbot, tries to detect Zolard, which are other IT bots. And if it finds them using various techniques, it then kills the process and deletes them. So this said, we at FortiGuard decided to start a project to study what Mirai is doing and how it's evolving, because we've seen there's been a huge increase in the frequency of these kind of attacks recently. So we started the Kai project, that's for Kilo IoT botnets. We started recently, a couple of months ago, and we wanted to try to identify as many different variants of Mirai and study them to see what's new. And once we identified these new variants, we tried to collect all the different C2 servers, the download URLs, to then blacklist them. Since we started, we collected roughly 4,000 different samples, and in these 4,000 samples, we were able to identify about 50 different variants. From these samples, we were able to find 400 different URLs. We blacklisted them, and then also identified 10 different, a bit more than 10 different exploits used in these new variants. To do that, we set up a honeypot. The honeypot is a low interaction honeypot in the sense that it doesn't really need much to communicate with the bots when they attack. So we just log the telnet commands that are run. We log the download URLs, and we download the samples. This is, again, pretty well drawn by me, but this is the structure that we have. We have a virtual machine running and a host machine that are running the two parts of the honeypot, and the guest OS is running the agent that acts as a telnet service. Then we have the host machine that is running the backend to actually analyze and log everything. They are connected to a router within the test network that gets all the traffic routed from an external router that is getting the traffic from outside from the internet. So once we collected all these samples, we needed to find a way to identify and differentiate between the different kind of families. So the first thing that we identify as one of the flags is the configuration options. Configuration options is the table that has all the different values that are used by Mirai in its functioning. So this table is present throughout all the different variants, but it does suffer some changes going from one to the other. Obviously, the CCs change, but also sometimes we'll get new entries for new functions or new services that offered by the new variant. Another important thing to give importance to is the table key. The table key is used by Mirai to obfuscate as strings. The way it does is pretty simple. It gets this 4 bytes, that beef here, and on the left it's the original. It XORs them together and obtains one value that will then be used to obfuscate the strings. This was done in the original and remained used throughout the first almost year with very minor variants. And then it was the first thing to be changed when new variants that were trying to do something more, something different. They started to change that. As you can see, they have like way less pronounceable options, for example. And this, as I said, was the first thing that was changed, and that was like a first indicator that someone was actually looking at the code and not just getting it and using it. So to solve this little problem, we created some IDA Python scripts. We have these are the two main commands that we use. The first one is the ID. So basically, it just gives us the key that is used to XOR. It's a 1 byte, so there are not many options. So we just brute force it. It doesn't take that much. And the second one is str, which deobfuscates the strings and then prints them. The name of the different families is given by the last string that you can see here, bin busy box. In this specific case, this one was part of the Okiru family, and this string is used by the bot to check that it has actually obtained access. It will run this. Bin busy box just allows to run like Linux-like commands, and it will get, if it is logged in, it will get an error because Okiru is not an actual command, and then we'll check if this error has actually been received, and if it has, that means that the bot has, the telnet attack has actually happened. There are many other things that we like to look at to have some idea if there's been a modification. We call them Easter eggs. They're called safe strings in the original code, and they vary from random sentences like "I love chicken nuggets" was one, and then others are just very foul things about researchers, which I'm not going to repeat. And then this one specifically is my favorite. It was in the original, and as you can see, it's a YouTube video, says on the top. And obviously, I had to check, and I was rickrolled when that happened. And it happens every time. It's always there. I always check it. That's the nature of it. So this is a kind of a heat map of where the C2 servers that we identified were. The darker, the more. So from these 4, USA, Netherlands, Russia, and China, kind of had, I would say, like 75% of the hits. And then there were some others from some countries in Europe and Canada, and stuff like that. So this being said, what are the interesting variants that we were able to identify in Mirai? So this is a timeline of the various variants. Every yellow line is a new variant. And it started in 2016. And Mirai was the first, obviously, and there were no real modifications of it for a while, let's say 4 or 5 months. Then the first one started to appear. You can see memes or objmpern. And these ones were really just changing the credentials used to updated new ones that were discovered. The first big family to come out was Masuta, which still wasn't very different in terms of the code, but it just happened to be more frequent. So it would pop up way more than the others, which would be like once in a blue moon. Towards the end of 2017, we started seeing a bigger amount of new variants popping up from time to time. So Satori, for example, was say that it came to light in December, but the first samples actually started circulating in August of 2017, and it was the first found to be using a different kind of propagation method. And then there's just I named a few there, but there were so many they just didn't have the space to do that, to do more than that. So as I said, Satori also goes by the name of Okiru. It depends. It's a debate. It changes the name in the strings, but the code is usually the same. The exploits are there, so we just group them together. It is believed to be coded by Nexus Zeta. Nexus Zeta, and that is due to some strings that are found in the sample and some claims that have been done by a user going by either Nexus or Zeta on different platforms, hacking forums and stuff like that. It is right now, as far as we know from our studies, the most popular mod of Mirai in terms of quantity. And it has the difference between Mirai and this one is the load mechanism and the propagation. The loader is actually embedded in the bot. It does not rely on an additional server side loader. And in fact, it uses exploits to spread, which is very different from Mirai, which, as I said, used brute force. And is also the first one that we encountered actually starting using packing software like UPX. The first version of Satori that was kind of interesting appeared in December, was detected in December 2017, and it included 2 exploits. Then in the month following that, in January, there have been 2 other exploits that have been found in Satori, and I don't have it in my slide because it's very new, but there was a new one last week that appeared. So these exploits, so this is a little part from the IDA of the first sample with the one with the 2 exploits. As you can see, the bifurcation will either scan port 52869 or 37215. And that depends on a randomly generated number. It doesn't really have anything to do with the scan itself. It's just 50-50. This is the first exploit. Is a 3-year-old exploit targeting Realtek devices. The actual exploit is relatively not important. It's just a way to get access, to get a shell, and then to download the bot. What is interesting, not with this specifically, but with the second one, is that it was a 0-day when it was discovered the first time in December. And this tells us that the developer behind this is committed in some way. It either able to create a 0-day or is able to get access to one. And this was the first kind of real commitment to these kind of things, because before it was just like copying and pasting the code, and this one is an actual modification. The third exploit is a different one. It doesn't actually increase the spreading of the variant, but targets Claymore. Claymore's the Ethereum mining software that runs on Windows, and basically the IoT device would try to scan for vulnerabilities on port 3333. I mean, scan for response, and then try the exploit. And if that succeeded, it would basically change the wallet destination of the mined Ethereum. And last time I checked was halfway through February, and I think this wallet, which is the only wallet that has been found. So there's not multiple people trying to do this, or they're not trying to change the wallet. It's always the same. It was about $5,000, something like that. So not much, but still, it's a way of making money out of Mirai in a different approach. This is the last exploit that I have here, and it's interesting because this one is not just like a copy and paste. It's a chain of exploits for Wi-Fi cams. So this chain would obtain the credentials first, and then we'll try to use these credentials to run the code to download the bot again. So it's again a spreading mechanism. The second family that I want to talk about is Mazuta. Mazuta is as I said, was the first real modification of Mirai. It was the first big family. And at the beginning, it was just a modification of the original code with some different XOR keys and different credentials. It has been popping up more lately in January, and it has started using exploits as well. It is also believed to be coded by Nexus-Zeta for the same reasons that I said before. It still has the same strings. It's been claimed by this guy on Twitter, for example. And it uses specifically SOAP exploits, mostly. They have two targeting D-Link routers, one targeting Zixel. And again, they would just get the access to the IoT device and then run the code to download the bot. The last variant that I want to talk about is called OMG. OMG is, the name actually was OOMGA, as you can see on the right, but really didn't roll off the tongue, so we went with OMG. We discovered this last month, 45 days ago. And the first, doing the retro hunt, the first samples appeared in 2017 in July, but it was still going under the name of Mirai. So they didn't change that, and that in December they actually started using a different name. In terms of the way it functions, is very similar to, it's actually the same as Mirai. The attack module, the killer module, scanner module there, and it uses brute force to spread. But it offers a new function, which is it allows the user, the attacker, to turn the IoT devices into a proxy server. The way it does is using 3Proxy. 3Proxy is an open source proxy server set that's available on GitHub. And basically, the way it chooses to use one or the other is through an input given by the C2 server. If you receive a specific message, it will switch from one mode of operation to the other. If it's in proxy mode, it will generate two random ports, one for HTTP and one for SOCKS. And then it will add these two ports to the IP tables, to the firewall, and basically allowing traffic through these two random ports. It will run its proxy, it will change the exchange of traffic, and then when it's done, we're receiving another message, and then it will shut down and delete these two rules, not allowing any more traffic to go through. So obviously, it would need some kind of interaction. It would need some kind of setting up. Obviously, that's not possible, so it embeds the whole configuration that it would need otherwise, and it's embedded in the code. When we started analyzing this this sample, the C2 was already down, so we couldn't actually contact it and have a kind of communication. Everything that we know is based on static analysis. So what we think is this was simply a copy and paste of the GitHub code into an already existing malware and used as an, let's say, like a testing, I would say. But this is showing that there is a direction in which these things are going, and in the future, these things could be used to have more intricate uses. Like, for example, you could use them to create a decentralized C2, be like more resilient on takedowns and stuff like that. So to wrap this up, Mirai is it's a botnet that is not being around for that long. It's been around for about a year and a half, and it started as a very well programmed botnet, but not that resilient, and had very basic ways of hiding himself. Has very basic obfuscation. It was using a kind of basic way of spreading, which was at the time the most effective. Although, like in time, in the past year, this has changed. The propagation has become a more targeted one. It started using exploits instead of using just brute force. It uses known packers, UPX for example, so slight modification UPX, and starting using creative ways of monetize. For example, the Ethereum mining exploit is an example. The proxy service to offer to your users is another example. So we expect this to continue, this evolution. There have not been real modification of the core functionalities. The proxy was probably the most different, but it was still the same kind of base code with an addition, with a copy paste of this code. But the more time passes by, the more people realize what the reach of this botnet is. We expect more developers to start tinkering with this, and the more people start to work with it, the more it gets on. So we'll also probably likely see more exploits because, as I said, the way Mirai works is try to shut down every other botnets to infect it. So most of the devices that were targetable by brute force logins probably have been in some way compromised. So what remains, what is still up for grabs, is the ones that are not vulnerable to that. So to get to them, there need to be a different way, for example, exploits. So in short, Mirai is definitely winning the war with other botnets because of the killing, because of the just the modularity it offers, the fact that it's open source basically, and it's easy for everyone to just pick it up and deploy it. And it's also so vastly modular and compatible with different architectures that it's just we don't see this going anywhere unless something else comes by that just revolutionizes the world of botnets. So that would be it. If there are none and you just want to later do that, these are the emails of me and my colleagues, and these are our Twitter handles. So you can just shoot us an email or tweet at us, and we'll be happy to answer.
Just one quick question.
Yes, sure.
Do you expect for the future something similar to a patching or hooking bot, just to take advantage of an already existing infection, just replacing addresses and replacing command and controls addresses and these kind of things, not to implement any functionality, but steal from other botnets?
Well, regarding Mirai, as I said, it's hard to do that. You would need to rely probably on exploits to get to the core of the bot. So it is possible, and but I don't see that happening on a large scale, but more of a targeted one. So probably it could happen, but it wouldn't. I don't think it would destroy Mirai in the way it is. Okay.
Any other questions? Oh, there. Sorry. Right there.
Is it on? Yep. Hi.
Yep. Stand up.
Just wondering if there is any...
I have no idea where I'm looking. Sorry.
Like
Sorry.
Any evolution in how manufacturer secure by design their devices, Internet of Things devices?
Yeah. So obviously the IoT environment is a relatively new thing, and it has been like the the buzz. Everyone wants to talk about IoT in the past 2 or 3 years. So what happened is that many producers of different hardware wanted to be part of this. So what they did is just pushed out something that would compete with other people. So obviously security was never actually looked at that much. So that's why we get the brute force. The brute force comes from that. Like the fact that the brute force login is so effective is that most of these devices are just kind of crappy. What they could do is definitely like invest some money, or it's just as simple as forcing the user to change the credentials at the beginning. This is what we could say for the brute force part. The exploits, obviously, that's just how it is. You can really say, let not have vulnerabilities, because that's what everyone tries to do. But then again, you just need to work harder on that. Okay.
Final question, Mark.
Nice here.
Okay, thanks.
Nice coverage about Mirai botnet. I have one question regarding the honeypot part.
Yes.
Can you disclose a bit which challenges you found trying to build a honeypot, or I mean, you use something open source, or?
Yes, yes. So we used an open source honeypot called Cowrie, if that helps. And so it is like the hard part is being able to find more. If you don't know, but Cowrie is a very easy to deploy thing, so that wasn't very difficult. The difficult part is having something that gives you more. We have a telnet honeypot, because that was the way it was developed at the beginning. It was the way it was spreading, and we are at the moment studying a way to have obviously like supporting more protocols, focusing on different ports as well. But that is the big question: is how can we get as much as we can and not just limit ourselves on telnet, for example? And that's a good question, because we don't really have an answer to that at the moment. But so yeah, like the big thing is to be able to be aware of all the exploits, for example, that run on different ports. But that, I don't know. I don't have an answer to that. We're working on that. We're trying to develop something nice on that.
Thank you very much.
All right.
Okay, no more questions.
Okay.
Thank you so
Thank
much,
you.
Dario.